Welcome back, my friends. This is William M. Briggs. This is another episode of Uncertainty and Probability Theory, the Logic of Science. We're up to episode 55. We're going to have sort of an informal chat today about models and reality. The first 54, plus a couple of other interstitial lectures I did, were all on how to understand uncertainty. That was it. That was everything. How to understand uncertainty. And not so much on modeling and not so much on the ontology of things, on the epistemology of things, because that's all models are. Models are the epistemology of things, understanding how our thoughts work in understanding reality and putting measures to reality. Really what we want in science is to know whether or not the causal aspects of our observations are true. And remember, cause has four aspects. We have the efficient cause, the thing that pushes something; the material cause, what are things made of; the formal cause, what is the form of the thing in operation; and of course the final cause, the cause of causes, the reason for things, the real why behind all things. And of course, science has abandoned most of these and is focused on primarily the efficient and material causes of things. And eschewing the other two, especially teleology, has led science into corners, bumping up against ceilings, whatever cliche you like to indicate a stoppage of thought. And that's where we are in science right now. But it's worse than that. It's things are worse than that I let on. So what we're going to do now from the rest of the class is talk about models. We're going to build models. We're going to examine models. We're going to verify models to see whether or not they're good, all these kind of things. But we're also going to investigate how science does modeling now. And we're going to find an extraordinary range of shortcomings. And that's unfortunate, especially where probability models are used. There are an enormous number of over-certainties. I don't say outright errors. There are outright errors too, many of those. And I'm not talking about cheating. We're not talking about cheating. We're going to leave cheating behind, more or less, from now on. Cheating is rife and rampant. There's too much money in science, too many scientists and so forth, and the incentives for cheating are large and unfortunately growing. And so is cheating. All of that kind of stuff we don't care about. It's obvious that there are problems, and the solutions, I think, are obvious too. We're going to talk about the more subtle and deeper kind of errors. So obviously, as I said, science wants to understand the nature of things, which is to say the essence of things, and the full powers that substances have, for causal powers, and the conditions that give rise to when these powers can be manifested. Sometimes they can, sometimes they can't. We want to understand all these kind of things. So we want to know basically whether or not our statements, our propositions about the aspects of these things are true or not, or how certain they are given the evidence that we have. And that's what we spent a whole year, more than a year, building up to, how to understand statements like this. But we also want to know, well, if I have a knob in nature and I turn it this much, I get this much of an effect, and if I turn it even more, I get even more of an effect, or possibly even less of an effect. That's a goal too. That's understand. It's the same question, but put into different terms. So more or less we have whether or not propositions are true, or to the level at which they're true, and to the strength of the causal strength of things, the strength of association and so forth. Those are great goals. Those are terrific goals. Those are the very goals we have. And it will surprise you, if you haven't been following up to this point, you're coming new to this, that those goals are not only not met, they're not followed. They're not even attempted in classical statistics, frequentist statistics, Bayesian statistics, and even in physics, where these type of models are used, and they're used all the time in physics. I have a picture on the board there, a cartoon. reality is enormous. Reality is the world. The reality is everything there is. And we have models, and there's absolutely nothing in the wrong at all with models. And models are simplifications of the world in order that we take portions of it that we think are true, correlations, or even some causes that we know and conditions, and we try to understand how the model, how the world can work through these models. That's a noble goal too. But the problem is the focus has become interior to these models. We have statements saying models are good when the models themselves are judged beautiful. Not how well the models accord with reality, not how well they predict reality, not how well they describe reality, but how well models themselves shine in the interior. All of this idea, we're going to talk in depth about hypothesis testing and its frequentist and its Bayesian form. All of this is nothing but statements about the interior, about the guts of models. You'll hear these terms: significance. What is significance? Significance is a measure of how good the model looks to itself. We'll hear terms like parameter estimation. Parameter estimation are merely statements about the interiors of models. People have got so good at the math of these models that they have forgotten that the models are not the goal. The models are not the goal, but the models have become the goal. What we really want is to talk about reality, and to the extent that models can help with this, and they can, we should use them. Otherwise, we should speak only of reality, or the bits of reality that we know, and those bits we're uncertain about. We can use probability to quantify that uncertainty sometimes, and sometimes uncertainty cannot be quantified. We've done all of that kind of a thing. And so, and I promised you many times that we will be talking about parameters and so forth. In the interior of these models, almost all of these models are parameterized one way or another, just mathematizations of numerical models with these very useful parameters and so forth. And I tried to give you an indication that we can find them from first principles. We can deduce them, and this is a wide open field because it's not been done for very many models, but we can deduce where they arise from finite, discrete processes where everything is observable, and then we could pass to the limit and where the parameters then become unobservable and on the continuum. Nevertheless, still useful for all kinds of numerical approximations and so forth, and we should absolutely use those approximations, but keeping in mind always that they are approximations and not statements of reality themselves. The problem comes in, and as I've mentioned more times than you can count, the deadly sin of reification, or reification, in which the model becomes realer than reality. We're going to meet lots of examples of this. My favorite are any kind of scatter plot. We'll go through lots of examples of these. Any kind of scatter plot in which the line through it becomes more prominent than the data, and the conclusion will be, you know, men are taller than men are angrier than women, and all kinds of nonsense, sociology nonsense. I can't even think of examples. I should have come equipped with examples today. But the line itself that they've drawn through the data, it becomes realer than the data itself. The data kind of loses focus when we see these lines in time series and everything else, and all of a sudden, because the math is concrete and real, and it takes some intelligence to do these things, and then we congratulate ourselves on our intelligence. We congratulate ourselves too well. And so these things become realer than reality itself. And we're going to try to guard against this, but I promise you, you're not going to. You're going to fall prey to the lure of the p-value, to the beauty of these models, and to the niceness of all the ways you can manipulate them and convince yourselves that your abstractions from reality are realer than reality itself. This will happen to you. Even though I've warned you, I don't know how many times, and I'm going to warn you as it's happening, it's still going to happen to you. That's how powerful the effect of this, all this stuff is. So I can give you some examples. Let's talk about, you go to a doctor and there's two pills for the same disease, supposedly, and you want to know, you're asking the doctor, which one should you take, pill A or pill B? And you want to know, that's what you really want to know. What's the probability you get well if you take pill B, and what's the probability you get well given pill A, given the particular evidence before us, the bits about you, your age, the background measurements we have on you and so forth. This is exactly what we want to measure. We want to know the chance you're going to get better or worse, or is pill A better than pill B or vice versa? Well, we can't tell using classical statistical methods. They're not designed to tell. Instead, they're designed to tell something about significance, which is just a measure, internal measure to the models that has no bearing on reality. It doesn't answer the question. What's the chance you get better if you take this pill? Doctors can't tell you. They cannot tell you. I mean, they can make up a guess, but they can't tell you. They cannot tell you using the apparatus that statisticians have set up. They can tell you that the probability of seeing data more extreme than was seen in an experiment, assuming the pill doesn't work, they can give you that probability. So assuming the pill doesn't work, here's the probability of data that nobody saw in no experiment that was ever done. They can tell you that, which is, of course, absolutely useless information. What you want to know, what's the probability is the pill going to cure you? Well, then you go to the Bayesian, and the Bayesian says, well, I can't tell you that, but I can tell you the posterior distribution of the parameterized model I have on this has a credible interval that doesn't, 90% credible interval that doesn't include 0. Aha! So what? What has that got to do with anything? These modelers forget that you could be absolutely, positively, 100% certain, locally certain, conditionally certain, about the interior guts of all these models, but still know nothing about reality. They don't tell you about reality. You ask these questions about reality, they won't answer questions about reality. It doesn't sound real. You're going to say, that's not true, Briggs. That can't be true. These people are smart people. They wouldn't do that. There's too many people doing all these things. I'm sure you're wrong. They must be answering questions about reality. I promise you, I'm not wrong. This is just the way it is. They do not speak of reality. They speak of the internals of models. You want to know about reality, they will not tell you because they can't. They don't know how. There's a handful of people out there that do this. I'm not saying it's nobody, but there's not that many. This is to AI's great advantage. I often say this. At least those people who do AI. There's all kind of overblown hype, grandiose promises, and that computer scientists are just prone to. They're forever promising the world and failing to deliver and forgetting about their fast promises. But that's just part of the nature of their beast. But at least they, when they build these models to talk about reality, end up trying to talk about reality. They might not get it right. They may be wildly overconfident themselves, but they're at least answering the question. They may be answering it badly, but they're answering the question. You don't get those questions answered in any kind of probability models and so forth. And it's the same in physics. I mean, you talk about particle conformation. Somebody posits a new particle that's going to carry some obscure force that was just invented to explain some anomaly, because they can't break out of the old way of thinking about ontology. But that's a whole other question. But they'll use statistics. Well, we have a 6 sigma, or 5 sigma. What are you talking about? They're talking about significance and so forth. They're not talking about predicting the values of things. They're not talking about the prediction of value of reality, about what these particles will do and so forth. They're instead giving you measures that are unrelated to the world at large. And I know that doesn't sound quite right now, but I will prove it to you. I have all of this stuff. The strategy is, and what you'll almost rarely see, very rarely see anymore in papers, is the data themselves. if you're dealing with some kind of simple sociological question where you've tried to quantify the unquantifiable, namely you you've concocted some sort of questionnaire and you're scoring the answers on these questionnaires hoping that you could plumb the depths of some uh, uh, subject, you know, like happiness or depression or something like this. You're trying to quantify this thing that really can't be quantified, but you're putting numbers to it, and that's a problem right there. We'll talk about that. But supposing those numbers are reasonably well associated with the underlying reality, uh, then you want to do some kind of statistical modeling on this. Don't. The best thing I can say is don't. Don't do any kind of modeling on it. Just do the data. Display the data. Display the data the best that you can. And we don't have to have a formal model of what's going on with the data unless you're going to make predictions about how reality is going to be if conditions are in such and such a way. So you're talking about income and race or something like this. Just plot income and race. You don't have to have lines through things. You don't have to have all these complex measures and announcements of correlation. You could show the data. I mean, there's all kind of strategies about showing data, and that's an art. There's no question about it. That's an art, and there's lots of difficulties, especially when things become multidimensional and all that kind of thing. I'm not saying it's an easy task, by no means. It can be quite difficult, but if you're not showing any data whatsoever, and you're giving out results merely in the results, merely descriptions of the interiors of models, you're not doing anybody any favors. You haven't done anything. You've talked about how good a model you've picked for your own benefit. You haven't said anything about reality. Why not just show the data? I've looked at so many studies. I can't tell you how many studies claim this or that substance in the environment is associated with or linked to some disease or another. We did this a while back, if you remember, in the epidemiologist fallacy. These papers, they come out almost continuously. They almost never show the data. They never show the data. They show the summaries of it internal to the models that they use. All we have to do to make any kind of convincing argument is show what it is that you think you have found. That they don't show data and instead just show you the results of models is partly based on the custom, because that's what everybody does. But it's also because the picture of the actual data of what they took is often extraordinarily loose. And you think, how can anybody claim a signal of this kind of stuff? And you've seen all these kind of blobs, just blob data that somebody has drawn a line through, and they're almost comical. But the way hypothesis testing works in a Bayesian or frequentist way, if you just collect enough data, you're going to reach this magical state of significance. And so you're going to be able to tell these tales. It doesn't matter how ridiculous the plot is, actually. Just the more data you collect, the easier it is to proclaim that your model has reached the plateau of significance. And I'll describe what I mean about that when we get to lots of examples. And I'm going to go through all these things. And if you don't believe me, once you go through this lecture, if you don't go through this lecture, just ask, particularly if you're in academia itself, after I give you the actual definitions of things. I'm going to tell you exactly what a p-value is and significance is. I'm going to tell you precisely what a confidence interval is, and more precisely what one is not. And I'm going to tell you what a credible interval is, and more precisely what it is not. And I'm going to tell you how to verify models and all that kind of stuff. And I want you then to go to your favorite academic and ask them to define what they think a p-value is, or a credible or a confidence interval, any of these other measures that people use to focus on the interior of their models. And you will see that almost always they will get it wrong. Almost always they will get it wrong. They will have a number of beliefs that are just plain false. We've talked about frequentist probability many times in interpretations of probability. And I've told you that nobody is, there's lots of people who claim to be frequentists when they posit their models and they use probability and so forth, but absolutely nobody is a consistent frequentist. And I can state that with absolute certainty. There's nobody who is a consistent frequentist. It's like meeting somebody who claims to be a perfectly consistent solipsist. The creature only exists on paper. Nobody really is one or can be one. Just like nobody is really a nominalist, although you can claim to be one. There's lots of claims to be these kind of things, but nobody in practice can be any of these things because the definitions always fail at some point. And we talked about all that frequentist stuff before, but I'll give you lots more examples and all this kind of a thing. So that's basically it. We've reached the point where even this is now seen as a benefit. Some physicists like David Deutsch and others and Sean Carroll and so forth, they point to the glory and majesty of their models as proof that their models are correct. I had a guy tell me on Twitter this morning, this Sabine Hassenpfeffer, whatever, she was going off, frightened of AI as people let themselves become, and said, well, the criticism is, she says, that AI is just a model. Is just carrying out code, carrying out instructions. She says, well, the brain is just a machine too. And that's, of course, absolutely false. They have let their models take over reality. And the way things comport to their models, the way they go out and find observations that comport with their models, and then they ignore all other observations. And they say, therefore, because these observations fit my model well, therefore, model consistency. This is exactly how they do it. Internal model consistency, the glory and the symmetry of the math. And people like that Hassenpfeffer should know better. That's a beauty criterion. That doesn't necessarily mean it has anything to do with reality. Reality can be very ugly and chaotic and so forth. So that has nothing to do with the way models should be. But they use model consistency and model self-consistency and so forth as, to them, proof that the model then describes the world. I've said this a million times to you too, and I'm going to keep saying it, that all of us are very good at finding evidence which confirms the theories we want to believe. That includes scientists even more than anybody else because they're smart people in general, less so today than they used to be. But they're very good at finding evidence that can support the theories, the models they have. Remember, I use no difference between, they do, I don't. It's my eccentricity, I understand this, between a theory, a model, and a law, and all these kinds of things. I think they're all the same. And I've given my reasons why, and we'll go through them again and again when we talk about specific models and so forth. But that a model fits, that a model is self-consistent and so forth, is in no way an indication of that it's good. And these scientists are very good at finding, however, proof that comports with the model, but they're very bad at finding evidence or finding arguments which discounts or disconfirms their beliefs. This is why they just can't do it. And because, for one thing, it's painful. It's always painful to give up a belief. There's some mental anguish that's caused when you give up any kind of belief. And no one wants to do that, especially one in which you have invested a long part of your life. And a part of yourself is wrapped up in these kind of things. That's why we have all kind of nonsense passed around in politics and so forth. When it becomes your identity, as the current slang goes, it's very difficult to give that identity up and change into something else. Although a lot of people are very good at being chameleons, they just want to be noticed and so forth. But that's an entirely different phenomenon that has nothing to do with science modeling and so forth. So model internal consistency and everything. This is a nice criteria. It is a necessary criteria to make a good model, but it is far from being sufficient. It is almost the trivial basic consistency which if that isn't met, the model's not worth pursuing whatsoever. But that's where things stop, and that's where we run into the problem. So we're going to not only build models, we're going to learn how to verify models. And that's the slang that's used, the jargon, I should say, verification of models and so forth. That lets us know whether or not the model we've built has any use whatsoever. We're going to learn how we can distinguish real cause and real conditions from correlation. The practice has arisen where correlation becomes causation when every scientist knows it's not true, that causation does not logically imply causation. The belief is when the correlation is my correlation, the one that I cherish, it therefore is causation, backed up by significance and these internal model glories and so forth. So we're going to go through all of that. This is just and I haven't proven any, I've proven lots of this stuff about probability and so forth. We did 54 other lectures plus a couple others on top of that. And a bunch of what are the chances and so forth to prove all these the arguments about probability, what uncertainty is, what probability really is, and how we calculate uncertainty when we can, and all that. We've done all that, and now we have to apply it to these to scientific models and so forth. So we're going to do it the right way, and we're going to do it the wrong way. You have to do it the wrong way to learn how to be able to read papers and things in the scientific literature and so forth. So if you're wondering, I haven't got to it here now. Well, you're right, I haven't got to it now. We're going to start that next week. This is basically, we did the 101, now we're doing the graduate level course and applications and so forth. So this is like the introductory class for that. I should name it something else, but I am the world's worst title writer, as regular followers and listeners would know. So I'm not able to do that kind of a thing. All right, that's it for now. I'm going to post a longer extract of uncertainty on the wmbriggs.com and wmbriggs.substack.com, in which you can read about this introductory stuff in detail and so forth. And next week, we really do start all of this stuff, modern modeling, how it shouldn't be done, but is, and how it should be done, but isn't. Thanks much for listening. I appreciate everybody who has stuck around this far. It isn't easy going, especially with me, I know. Thank you.